Okay, we're ready when you are, and then we'll work on the focus problem.
All right. I don't have the other mic. Is there another mic here?
You can just hear. You can talk into
On the
that.
podium mic.
Okay. You going to give me a countdown?
We're all set.
Okay. Well, good afternoon, everyone, and welcome to the first security seminar of the spring semester. We're very happy to have all of you here, and those of you who are watching either the recorded version or otherwise. Today's speaker is Dr. Simson Garfinkel, someone I have known and worked with for over 15 years, and it gives me great pleasure to say it's Dr. Garfinkel, because pursuing that degree has been a goal of his for some time, and he's done some really remarkable work over the years in a number of areas, including security policy, privacy policy, technology issues of many different kinds. And most recently, he's been doing work in two areas related to cyber forensics and to security and usability. And today he's going to talk primarily about the cyber forensics. And so without further ado, let me introduce Dr. Simson Garfinkel.
Thank you. So I have too many slides, so we'll have to go through them quickly. Here here's a picture of 200 hard drives. And the question you might want to ask is, which of those have my email address, Simsong at Media? Now, that's a hard question. So one way that you might solve that is you might take each of those drives onto a computer and image it manually and go through it with tools. And that's the way most people would do it today. I'm going to be talking about new tools and techniques that you might use to do that kind of analysis, and additional analyses that you can do with these kinds of tools, which are designed to work with large numbers of disk drives rather than one or two disk drives. Can I close this door? Okay. There we go. So first I'm going to talk about the drives project, and then I'm going to talk about the traceback study, and finally I'm going to be talking about cross-drive forensics. Now, this is a computer here that I purchased at a used computer store in 1998. And I was doing a project. I needed 10 computers, and they sold them to me for $10 each. And it turned out that it was the file server for a law firm, and that it still had client confidential documents on it. And the other computers also had really interesting information. One had mental health records. One had home finances. One had a draft of a novel. And the real question that I wanted to know was this a chance occurrence or something that happened frequently? I had a special relationship with the owner of the store. Now, hard drives have this special problem for computer security. They don't forget data when the power is turned off. And they contain data that's not immediately visible. You can look at the hard drive. It's very hard to audit it. And hard drives are remarkably stable. They're probably the most stable thing we have in computing. You can take a 15 or 20-year-old hard drive, plug it into a modern computer, and read the files. Because the file systems are now, the Mac and Linux and PC all support the old fat file systems. And the ATA interface has been remarkably stable over time. And the power connectors are still the same. And this is very different than tape drives, where even a 5-year-old tape cannot be read in a modern tape drive. And there are a huge number of hard drives out there. So this graph, which is pretty much current data, you can see that in this year, there'll be something like 375 million hard drives shipped. And there'll be a little more than 200 million hard drives retired. And each one of those retired hard drives is a security problem, potentially. Now, if you physically destroy the hard drive, there's no problem. So this hard drive was punched with a machine that punches out the spindle. That's not good enough for classified data. This hard drive here was put in a blast furnace and melted and turned into ingots. That is good enough for classified data. It turns out that most of these retired hard drives are not physically destroyed. There's actually a lot of them that are sold on eBay. There's a large secondary market. Some of them are reused within an organization. They're given to charities. I found one charity that was collecting hard drives, actually whole computer systems from businesses in the Boston area, and sending them to India because they need computers in India. And I asked the people, well, how do you assure that the companies that give you these computers, that their data won't be compromised? And they say, oh, don't worry. We clean them off first. We install Linux on these computers. And I said, so you're not actually sanitizing them. You're simply giving the people who get them all the tools necessary to recover the confidential data that they might still have. Now, there have been roughly about a dozen cases of people who've bought used hard drives or used computers and have found very important records on them. And one of them, John Markoff, wrote in 1997 in the New York Times about this woman in Nevada. She bought a used PC, and it had 2,000 pharmacy records on it, prescription drugs, people in her community. And survey after survey says that Americans think that medical records are the most sensitive information that they have. And here, a pharmacy had sold basically a list of everybody who was depressed in the woman's hometown. None of those studies were really scientifically rigorous, so I decided to try to do something bigger. And so starting in 1998, I started buying used hard drives, and I'm up to about 1,000 of them right now. And what I do with these hard drives, they show up by UPS or USPS, and sometimes I buy them at used stores. And I have this machine where I image them. I copy the data that's on the hard drives onto a server. And this machine, you can see, can do 4 at a time. So I've been developing software that does this in a sort of production mode fashion. And then I compress the images and I store them. That right there is 900 gigabytes of storage, which is astounding if you think about it. I have basically 600 or 700 hard drive images stored on these 3 hard drives here. Now, I'm not looking at these exotic recovery techniques for data that's been written over once and you can recover this stuff that's there. You know, we hear about this secret technology and you have to rewrite multiple times. For the purposes of my research, if somebody just writes zeros over the disk, I can't get back the data. I'm just asking the disks to give me their data. And as an example, I'll show you disk number 70. So I purchased this disk for $5 from eBay from a Massachusetts retail store. And it had 541 megabytes of data, so it has 1 million sectors, because sectors are always 512 bytes long. And if you mount the disk, you see these 3 files, io.sys, ms-dos.sys, and command.com. And, but if you look at the sectors, it's got 1 million sectors, and it's 989,000 of those sectors contain user data, contain data of some kind. So what happened to this hard drive? Does anybody know? Yeah. Not quite. Yeah. Right. They ran the DOS format command. Now, the DOS format command makes a promise. And that promise is, warning, all data on non-removable drive C will be lost. Proceed with format. Yes, no. And it lies. Now, you might want to do a class action lawsuit against Microsoft. And in fact, the fdisk command is another technique that people use to sanitize their hard drives. I bought some hard drives at a used store, and I asked them how they clear them out. They said, oh, we do better than format. We delete the partition with fdisk. Right? So the format command on that on this 10 gigabyte drive with 20 million sectors, the format command overwrites 21,000 sectors, or 0.1%. The fdisk command overwrites 2,000 sectors. All it's doing is rewriting the partition table. That's one sector. But it actually does some checks other places on the drive to make sure that it's actually working. These commands will complicate data recovery if you're trying to recover whole files, if the files were fragmented. But they will not erase the user data. Now, I took that drive number 70. I created a file called 70.img, an image of drive 70. I did that with the dd command. And then I ran the strings command on it. And strings looks for printable strings. And the first thing we see here is insert diskette for drive and press any key when ready. So that's a bootstrap loader. And then we see your program caused the divide by zero overflow error. That's an interrupt service routine for the divide by zero. And then we see this thing here, OEM string equals NCR14. Anybody know what that is? Graphics mode 640 by 7 by 480. This is part of the Windows registry. So it has things that it would print if it discovers this device. Then we have IBM Antivirus Trial Edition. So you could look at what version of Trial Edition antivirus it has and actually learn when this hard drive was sold originally as new equipment. And then we have these medical terms. Insulin, ammantin, mannitol. So these are some medical terms that you won't even find online. You have to actually go to a medical dictionary. And I was able to determine that this hard drive came from a mail order pharmacy. And they had sold their hard drive. Eventually it had ended up here. But the original owner was a mail order pharmacy. So back in 2003, Avi Shalat and I published our first paper on this project, where we published the initial data findings of the first 150 drives that we analyzed. And we said, look at all the data we found. We found thousands of credit card numbers, financial records, trade secrets. Nothing military that we were able to identify. But we didn't look for the cause of why the data was there. We had some hypotheses, but there was enough. But why don't we hear more stories about people finding data on used hard drives? There's about 1,000 used hard drives a day being sold on eBay. So that's only 350,000 a year or so. But why don't we hear more of these stories? So one reason might be that most of the hard drives being sold are properly cleared. And another hypothesis might be that these disclosures are so common that they're just not even newsworthy anymore. And I don't think that either of those are correct. I think the third one's correct, that most drives sold are not properly cleared, but most people don't notice the data that these drives contain. Now, why would that be the case? Well, if you think about a hard drive and data on the hard drive, it's arranged in sectors. And there's some sectors that are used for directories, and there's some sectors that are used for files. But basically, they're blocks that are allocated, that are reachable from the root directory. And then there are what I call these brown blocks. They have user data, but they're no longer reachable from the root directory. And then there are green blocks. These are blocks that are all zero. And so what you'd like is there to be no brown blocks. You'd like for there to only be white blocks and green blocks. But this is what, say, a typical hard drive looks like after it's been used for a while, because the delete command doesn't actually delete the files. It just deletes the pointer to the file. Now, you can take those and stack them up as a bar graph. And we're going to use this visualization for looking at a series of history that might happen to a hard drive, where you have the files, the deleted files, and the zero files. When the disk comes new from the factory, all the blocks are zero. And then, if we format the drive, it puts some file system structures on it, but it's basically still zero. If we install an operating system, they're the temporary files that the operating system created during the installation. There's the operating system files, and it's still basically zero. Maybe we've used it for a year. We have more applications, operating systems, more deleted files, but still some blocks that have never been written. Now, if it's a student here at Purdue, you have a nice fast internet connection, and they fill it up with MP3s, and then it becomes time to get a new hard drive. So what they do is they format the drive, and they sell it. They give it to a friend. So clearly, if what's going on here is that people are just getting rid of their hard drives without even thinking about the problem, you're going to see a lot of drives where there's a lot of data that's recoverable, and a little bit of deleted data, and a little bit of green blocks. And that's what I call a training failure. People simply haven't even thought when they get rid of their drives that maybe the data is recoverable, maybe I should do something about it. But if you see a lot of brown data, then that's people tried to erase the drives before they disposed of them, and they failed because the tools lied to them. So what I did was I ran that experiment on the first 236 now hard drives. This is a slide from my PhD thesis. And I graphed them, each bar represents a different hard drive. And these are very small hard drives, and these are very big hard drives, up to 2 gigabytes. And the lines indicate that hard drives tend to be made at characteristic sizes. So this is like a 1.25 gig drive. Now, the drives that are green from the top to the bottom are the drives that were properly cleared before being sold. And the drives that are brown from top to the bottom are drives that were formatted, but were heavily used before being sold. And some drives you see are sort of a lot of white and then some red. And the story with those drives is that those drives were used and then somebody went through and deleted the user data files, but they left the application files. And they left the application files as, I guess, a present for the next owner of the drive. So if you look at this graph, you can see, there's a lot of structure here. Like there are all these drives here, they're all green. Those were all properly sanitized. Well, I can tell you that they all came from the same company. That company had a policy of when they sold their drives on the used market, they cleared them. But I bought one more drive from them, and it wasn't cleared. I bought it a year later after they were in financial difficulty. They weren't implementing their policy at that point. The company had changed hands, and they were in trouble. So here are the overall numbers. I bought 236 drives, of which 60 were DOA, dead on arrival. Didn't work. There were 176 drives image, of which 11 were zeroed, and 22 were clean formatted. They were zeroed, and then somebody had formatted the drive so that the future person, I guess, wouldn't complain that the drive didn't work because they didn't know how to format it. Not overall a lot of files, but a lot of data. And so the main conclusion here is that people are trying to erase the data, and the tools are lying to them. And so one of the areas of my research is, how can we improve the tools? How can we improve the operating system? It's got to be in the operating system so that this problem goes away. Now, and here's some supplementary material there. And what this slide is showing is that there is actually very little regularity. Even the drives that were properly cleared, there was no consistency. I got one from a company called Drive Guys, but two others from that company had data on them. There was one Virginia reseller. One drive they gave me didn't work. 3 were formatted with lots of data, and 1 was properly cleared. But to find out what really happened, I had to sort of become a journalist again. I had to go back and contact the original drive owners. Now, this is hard to do because I had to figure out who was the original owner. And then I had to get contact information for the organization. I had to find the right person inside the organization, set up interviews, and the whole time follow MIT's guidelines for working with human subjects. And to give you an example of why this is hard, I'll show you here. I wrote this program that sort of does a batch forensic analysis. It finds all the deleted files, and it gives them names so that you can talk about a file even after it's been deleted. And so there are all these Microsoft Word doc format files in this. It's like a 4-H resume, a resume to Marymount University, a resume to admissions counselor. Who's the owner of this computer? Every doc file is to and from a different person. Right? So it turned out that this computer was a public machine at a university. And that was hard to figure out because all the information led to different people. So I ultimately contacted 20 organizations, and here they are on the map. A lot of them were from California. I think that's because I was largely buying computers after the dot-com crash, and so that's where a lot of crash companies were. The leading cause, once I interviewed people and found out like what had happened in the custody, was a betrayal of trust. The organization was aware of the problem, they had, or the individual was aware of the problem, and they had trusted somebody else to deal with it for them, and they were betrayed. So this one up here, a woman, her son took her hard drive to a company called PC Recycle, and they promised him that they would recycle the hard drive, and they charged her some $5. And they recycled the hard drive by putting it on a table. And then I came into that store, and I bought that hard drive from that table for $5, and the hard drive was recycled. And that hard drive had her last will and testament on it. It had a Microsoft Word file with all of her bank accounts, all their web-based passwords, all her investments. And she was very glad that I called her up, because at least I got it and not somebody else. An auto dealership, they had their computers upgraded, and the consultant sold the hard drives on eBay without even telling them that that's what he was doing. And they just assumed that they didn't even think about this problem. They had trusted the consultant to do the right thing. Now, another leading cause was, in fact, poor training and supervision. I found a hard drive that was from an ATM machine from a bank in Chicago. And that hard drive had been formatted. And I called up the bank. And they said, well, we had all of our ATMs upgraded, and we hired a company to do it. And the contract said that they had to sanitize the hard drives. So we'll need to check into this, and we'll get back to you. Well, they checked into it. That company nobody does their own work anymore. That company had hired a subcontractor. And the subcontractor had been told to clear the hard drives, but hadn't been told how. And so that subcontractor used the format command. The supermarket had a policy in place at the time that the hard drive left the supermarket to clear every hard drive. But they didn't audit. and it may be that the person who was implementing the policy didn't know the right way to do it. This California electronics manufacturer, again, they had a policy. They were aware of the problem, but the person doing it just not properly trained. And then sometimes the data custodians just didn't care, and this was largely organizations that had gone into bankruptcy, and they felt that they had no responsibility to the people whose information was on the hard drives. There was an internet software developer, and they were just happy that the reseller would come and pick up the computers for free. Computer Magazine, they had layoffs, and they basically said, well, we don't have confidential information, and if people were storing their own personal stuff on their office computer, that's their own tough luck. Now, there is no regulation on resellers right now, but if we had regulations on resellers, that would actually solve this problem. In this country, you're not allowed to sell toxic materials unless you're regulated. You follow the rules, and there are certain people you sell it to, and you can't, it has to be in special kinds of containment. But we allow people to sell hard drives that might have toxic data on them because we have no regulations requiring that the resellers assume some sort of responsibility. In 7 cases, I wasn't able to determine the cause whatsoever. The mail order pharmacy, they just refused to talk to me. And under my terms through the MIT office, if they didn't want to talk to me, I couldn't force them to talk to me. Primary school principal's office, it was 10 years ago, and the principal had left. I had all these letters to parents of behavior problem children. All those children are like going to college right now or getting their first jobs. So regulation would have helped there too. One would hope. One would hope. Now, I did not check them out. Now, it's interesting that the techniques that I had developed for my study were really different than the techniques for today's computer forensic tools. Because today's computer forensic tools are based on the sort of one drive, one person, one report model. The drive is seized from a suspect's house, or it's seized in the part of the investigation, and there's this interactive user interface. You have an examiner, and they have hours and hours to look for the incriminating data. And here's an example of the encase user interface, and it will allow you to drill down in a Microsoft PST document and recover email. And this is great if you want to prepare a report for a courtroom. But it doesn't work if you have hundreds of hard drives to analyze, and you simply want to find the ones that will be most likely to give you good information. What is good information? Right? So for me, good information is stuff that shouldn't have been released. But for you, good information might be something else. So another problem with today's tools is that there are other problems that I kept coming up with. Like, this drive might have been previously imaged. And when you start dealing with hundreds of drives, keeping track of them and keeping track of their serial numbers and their images becomes a major problem. Just figuring out where to start. The tools that are developed for criminal investigations just don't work for this kind of problem. So I'm going to give you an example of 2 approaches that I developed. The first approach is to look for Microsoft Word files and try to determine the owner. You could do that with Encase today. You need forensic skills. You require complete documents if you're trying to identify the owner of the hard drive. But an automated approach that you could do is you could just compute a histogram of all the email addresses on the hard drive. Now think about that. If the hard drive was used for email, then the most common email address on that hard drive is going to be the person who was the primary user, because they're in the from and in the to of many, many of the email messages. So I thought, that might work. So the email histogram approach actually works really, really well, and that's how we traced back the majority of the hard drives. It was too hard to look for Word documents. Many didn't have Word documents. But when we did the email histogram, the first one at the top was the owner. And here's sanitized from disk number 51. Alice at domain1.com, her email address was on this hard drive 8,000 times. And she was the primary owner. Bob at domain1.com was somebody that she worked with. And domain1.com was actually the name of their company. And then Alice had another account that she also checked. And so we were able to infer that because it was the same username, but different domain. We didn't completely sanitize this. It appears that she was at Stanford Business School. and I could tell that because she's getting emails from their job info network. You can learn a lot about the owner of the hard drive and about the relationships simply by doing the email histogram. And what's really neat about this is you don't need to understand the file system. You don't need to figure out if it's a Macintosh file system or an ext2 or even a FAT or a NTFS file system. It just works. Neat technique. So what I'm doing now is I'm trying to develop a large-scale system for doing this en masse, and I call this approach cross-drive forensics. Forensics approaches that work across many, many drives at the same time. And the idea is you take in hard drives, you accession them in the field, you image them, and then you put the drives in what I call cold storage. You put them someplace where you won't need to deal with them, but you can recover them if you need them. The drive images go into a image repository. We run feature extractors, which go through that bulk data and capture different features. We throw that into a metadata repository. And then there are correlation agents that you can run over that data to come up with the hot drives. It's a nice architecture. And then you can augment it with information from other sources. So NIST and FBI have databases of hash codes of like known child porn, or there's a list of, say, known application programs. And you can use that to go against the metadata repository for things that you should especially look for or things that you don't have to look for. This gives you a way for rapidly looking over this whole sea of hard drives, and as new drives show up, to incorporate them to run the studies against them all at the same time. Now, what I call first-order cross-drive forensics, I apply this filter to each drive image individually, and I look for images that give the largest response to the kind of filter. And drives that have a lot of response are, by definition, interesting drives. So here I have a filter that looks for CCNs, or credit card numbers. And this is a funny graph. So the scale here is like 0 to 300, and then the scale here is like 300 to 40,000. And over that, say, 200 drive sample, each one of these bars represents the filter's response on a different drive. Red is unique credit card numbers, and blue is then total. So sometimes you see duplicates. So here we have a hard drive with a lot of credit card numbers, and here we have one. Here we have one with a lot. So maybe that's the first one to look at. And if you're like me looking for sanitization failures that are important, then hard drives that have thousands of credit card numbers on them are probably going to be important, because most hard drives just don't have thousands of unique credit card numbers on them. Now, the way that credit card number detector works is there are patterns that make credit card numbers easy to find. So they tend to either be blocks of 16 digits or 4 blocks of 4 digits. They are issued with well-known prefixes corresponding to certain banks. There is something called the credit card number validation algorithm. It's a simple checksum. It's one character. So any random collection of 16 digits has a 1 out of 10 chance of passing. And then it turns out that there are certain numeric patterns that are unlikely in credit card numbers but are very likely in other kinds of bulk data. So this one turns out to be unlikely because it has too many 6s and 7s in it, and there's sort of this progression. Actually, this is from an image file. So a lot of TIFFs and a lot of, for some reason, things that look like credit card numbers show up a lot in various file types. So I wrote this with Flex and in C, and here we are scanning over drive number 105. And there were 3,800 numbers that matched the typographic test. But when we selected out well-known bank prefixes, there were only 90. When we then selected out ones that matched the CCV1 algorithm, there were 43. I applied my histogram test to it, left 38. And then here is the example of those numbers in the data. Between the bars is what matched, and you can see, wow, those are credit card numbers. And then before it, actually, I didn't put in this is in the database. They actually tagged it with the name of the financial institution that issued the credit card. And here's the position within the file. And this is what I call my feature file. And this feature file is very useful for doing the correlations later, but you can also just sort of look at it and make a decision. Now, here's false positives. These numbers all pass the credit card number validation algorithm. They all have prefixes that could have been issued by banks. Before and after the dashes or the vertical bars are what's in the context. And you can see it doesn't really look like it was part of a real database. Those don't really look like real credit card numbers. So these are false positives. It's not a perfect algorithm. That's okay. So I ran the scan over the 2003 corpus of 178 image files. I found 47,000 credit card numbers, of which 15,000 were distinct. And here's the most popular credit card number. I found it 34 times on 30 drives. So that's not good. Like, why would you find that? So this is clearly a false positive. And you can see even the context is, this is the drive number, drive 6, 7, 8. The context is before and after the same. And so this could easily be from like a DLL that's part of the Windows operating system, maybe. Well, we could put it on a stop list. Say, okay, if we see it on all those drives, ignore it. Take it out of the analysis. So I do that and run the numbers again. And now the most credit card number, again, it looks like that. And in fact, the context, it even looks like it has some C code after it, a printf performed. So this stop list approach, I don't think is a good approach. It's the obvious approach, but it's a pain because you have to construct this stop list. You have to maintain it. You have to tune it for different applications. It's just too much work. It's more work than I want to spend. So instead, what I just do is I hope that my credit card number detector is good. I manually tune it up. I try to. That's why the histogram test is there. It seemed like a good test. But then I just hope that the majority of the positives are going to be legitimate positives and that the false positives will be lost in the noise. And in fact, they were. So this drive here, 5,000 credit card numbers, of which 1,300 are unique. This drive here, 1,200 credit card numbers, of which 286 are unique. This one, 31,000 credit card numbers. So then, once I have these drives to look at, I can look at them with manual tools, like encase or strings or what have you. And I did that, and I found that this is that hard drive from the supermarket. This is a hard drive from a software vendor. They're selling software over the internet, collecting credit card numbers. This is from a medical center in Florida, 31,000 credit card numbers, and then elsewhere, diagnostic codes, and elsewhere, billing units within the medical center. This drive did not have a file system on it. The drive was an Oracle raw data drive. So if you had gone into that hard drive with a tool like encase would not have been able to identify a file system, and all it would have been able to do is do string searches. And yet, that's one of the most interesting hard drives in my entire collection. So the second order analysis actually does correlations between multiple drives. It says, okay, can we find drives that have something to do with each other? And I was sitting at MIT with a friend, and I said to him, I wonder if any of our hard drives have credit card numbers in them in common with other hard drives. I wonder what that would mean. Well, so I built some technology, and I ran the study, and then I had to figure out how to visualize it. And this is the visualization. So this is the first drive, and this is the second drive. And the peaks are the number of credit card numbers that they have in common. And so all this noise down here, these are all the false matches from like the false positives. Every drive that had that thing that looked like a credit card number that made its way through. But this one here, that's 25 numbers in common. This is 13 numbers. This is 13 numbers. Let's look at them. Well, it turns out that these are from the same medical center. And what that medical center had done is that one drive is that Oracle data drive. Another drive was a drive that had a Unix file system on it, and it had source code on it, and it was their development drive. And they had taken live data from their production system and used it on their development system to do testing. And I found that automatically. Here, these are two drives from that same car dealership, the one I mentioned earlier. Now, the algorithm didn't know that they came from the same reseller on eBay. It found that out. Now, of course, there were other drives that I bought from the car dealership, it turns out, that did not correlate. So I'm getting lots of false negatives. I'm not finding all the correlated drives. On the other hand, I'm only doing the correlation with one thing here, credit card numbers. And I could correlate with other pieces of information. I could correlate with email addresses. I could just do the MD5 of every block and treat that as something to correlate on. And these came from the same community college. Now, I've written a paper on this, and it's in submission. And what's very interesting here is that these are actual real credit card numbers. But here on the community college and here in the dealership, they actually correlated on false positives on the credit card number detector, showing that it's not that they're credit card numbers that's important, the thing that's important is that it's what I call pseudo-unique information. It's information that you tend not to find in the wild, but if you find it in more than one place, then there's a high probability that the data actually got moved from one place to the other place. So other things that you can use, as I said, you can use message IDs. Now that's very interesting. Those are supposed to be unique per email message, so you can find out if two hard drives touch the same email message. Maybe because one person was sending mail to another person, or maybe because they were both on the same mailing list, or who knows. And as I said, MD5s have disk sectors. So what can you do with this? Well, you could identify social networks. You could test for inclusion in existing network. We have this drive from a suspect. Who else does that person communicate with? Or you could look for the dissemination of information. We have this PDF. Maybe it's a PDF of a manual. Maybe it's like that Al-Qaeda training manual. And we can look, take that PDF, break it up into each block, calculate the MD5 of each block of that file, and see who had those blocks on their hard drives. Even if they deleted the file and it was partially overwritten, as long as there are some remaining blocks. An interesting fact of today's file systems is that they always block align large files. So small files might not get block aligned because of the way these high-performance file systems work, but any file larger than 4K always gets block aligned. And so the 15th or 20th sector in that file will almost always be a unique disk sector. And if we calculate the MD5 of every disk sector on the disk, we'll find it. So this is pretty cool. And I talked about that. So reactions to this research. After the first paper was published, there was legislation that was introduced in July 2003, the Fair and Accurate Credit Transactions Act. And surprise, surprise, they put a requirement in it that companies getting rid of hard drives had to be sure the consumer records were removed. And I feel responsible for that, so I'm really happy. And if you go through the congressional testimony, it does seem that a lot of the news coverage that we had in January 2003 was responsible for that being put in. Another reaction was the Secure Empty Trash feature in macOS 10.3. And I interviewed the people in Apple's security group, and they actually added the Secure Empty Trash because of the paper that was published in 2003. And that's really nice. It's nice when you can have an impact on a company with research that you do. Unfortunately, they didn't do a very good job implementing Secure Empty Trash. It's implemented inconsistently. They implemented on the Finder menu, but not on the control menu for the trash can. It's really not even clear what Secure Empty Trash means unless you're sort of up on this stuff. And once you're secure emptying trash, you can't use the trash can. It's a very slow process. It doesn't happen in the background. But the worst part about it is you can't change your mind. If you accidentally empty the trash, and then you say, oh no, I should have secure empty trash, it's too late because the files are deleted. What the Secure Empty Trash does is it overwrites each file, and it does it at the user level. It doesn't even do it within the file system. So there may even be an interaction with the journaling file systems that the Mac uses. And I just don't know right now, but I'm doing some research on that. Now, macOS 10.4, they said, oh, well, we'll deal with that problem. It's as if they're reading my presentations and fixing their operating system. They added this button to the disk utility. It says erase free space. And what that does is it makes one big file. And the hope is that that one big file will take over every disk sector that hasn't been allocated to a file and will go into the one big file. And in this way, maybe you'll overwrite all the deleted files. So that's how you recover from accidentally deleting. But I'm not sure that the one big file approach works, and I'm actually doing some experiments on that right now. It seems to work well in most cases, but it does seem to leave some data behind. Of course, another thing people say is, oh, well, just use an encrypted file system. And in fact, macOS has a very easy-to-use encrypted file system. But the problem is that this encrypts all the files. And if the computer is left unattended, if it's like a public access kiosk, the file, it's still going to encrypt and decrypt the files. So you actually can apply the forensic tools to the encrypted file system. It just has to be mounted. And as long as it's mounted, it doesn't matter that it's an encrypted file system. Now, I believe that what we really need to do is to change the semantics of the delete command. So delete's never really been well defined. It sort of means that if an object is deleted, you can't find it with the old name that it used to have. But I believe that delete should have the semantics that the data is overwritten, so it cannot be recovered. And we've seen these problems in Word files and PDF files. We see in many, many cases that improperly implemented delete has resulted in data being leaked out. And so if I was going to have an agenda for what to do, it would be to fix the format command so it actually erases the disk, to make empty trash actually overwrite data, to make just delete when you delete a file, to have it be properly overwritten, to integrate this functionality into web browsers, word processors, operating systems. Like you have an option in many web browsers to erase the history file, but the history, it just unlinks it. It doesn't actually overwrite it. And then there are some usability feature problems that come up because of clean delete. So if you're going to have a clean delete or a complete delete feature, you then need to have other systems for providing people with better backups. Right now, forensic recovery is used sometimes for backups, but not all the time. It is a safety net for some people, and I believe that we should actually have better safety nets that have more have properties that we can clearly articulate and actually set policy with. Now, I'm also trying to see if my techniques will work if I scale up. So I've done the techniques with the 200 drive corpus and the 250 drive corpus, and I'm now expanding to a 2500 drive corpus. So I'm up to 1,000, and hopefully I'll be there by June. And there are these other approaches I'm looking for doing the cross-drive forensics. A lot of the tools that I've been developing for this work are generally useful, and I have released them all as open source. So if you go to afflib.org, you can actually download my drive imaging tools. And at some point, I hope to have a web-based database of hash codes that people can look up and give information. And then there's this real question about sort of the economics and societies questions. Like, who is buying these used hard drives? When I buy used hard drives on eBay, I actually lose most of the auctions. So I'm competing against other people. Who are they? And why are they doing this? There's a high failure rate, right? Something like 1/3 of my drives are DOA. So I'd like to know more about these organizations that are also buying used hard drives, and I intend to find out. And I'd also like to see if, since the passage of this legislation that Congress wrote for me, maybe there's been better compliance. And so I want to do time-based analysis. One of the things you can do with the cross-drive technique is you can figure out when the data came from. And so I want to graph sanitization practices over time. But to do that, I need more data. And so I'm collecting a lot more data. It's hard to collect this data. I have the largest unclassified data set of hard drive images in the world. And it is a data set that I'm happy to share with people if they're willing to agree to certain privacy restrictions. And I'm just looking for people to collaborate with. So any questions? No questions? Wow. So I either did a really good job or a really bad job.
You mentioned you didn't know who you were competing with in these sales, but do you have any external evidence that there have been there have been problems of identity theft or whatever that have been?
I do not believe that people doing organized identity theft are buying used hard drives on eBay, because it is too easy to get that information from other sources. You can just break into a bank and steal their credit card numbers. Like, we keep hearing of these cases, right? The credit card processing company, 31 million credit cards or something. So I don't think that I'm competing against the identity theft people. I think I'm competing against somebody else. I don't know if I'm competing against lots of individuals who are misinformed, or if I'm competing against a few organizations. I don't know what people are doing with the hard drives that they buy used on eBay. The only other organization that has bought significant numbers of hard drives on eBay for this purpose is a company called O&O Software in Germany. And I'm sort of collaborating with them, but it's hard because they're in Germany and I'm here, and hard drive images are really big. So they tried FTPing me their hard drive images, and it was not a good idea. But I don't know. And I'd like to do some web scraping of eBay's database to try to do some correlations on who the bidders and who the buyers are. Yeah?
Actually, I got a partial answer for that, so maybe you should
Yes.
Microphone on. So I have a friend who specialized at some point in data recovery, just for people who have old hard drives that fail, and they didn't do backups, and they're in that desperate solution, like OnTrack, like what OnTrack does.
Yes, yes.
And so they're actually a huge customer of eBay for having the old heads for the hard drive.
So that is, this is, there's a theory here that you can buy old hard drives to, do you know for a fact that OnTrack is a big customer?
I don't know for a fact for OnTrack, but for the French company he worked at, I know it for a fact.
So
because he was the buyer for the company.
So one of the problems is that there are so many different hard drives. I'm periodically contacted by people who want to know if I have a particular model number so they can get the circuit board. And that's what's called drive-independent data recovery, or changing the head assemblies. This technique doesn't work very well anymore. And it doesn't work. There's a paper, if you go to the forensics wiki, forensicswiki.org, there's a paper that talks about drive-independent data recovery. And the reason it doesn't work is that modern hard drives are really well matched between the head and the media and the storage capacity. When they're created, they figure out how much disk space they're going to have based on how good those particular heads are and how good that media is. And they basically decide whether they're going to be a 40 gig drive or a 60 gig drive. And they format accordingly, and they use coding accordingly. So you can't do the replacement operation anymore because it won't be properly matched. It works on old drives, doesn't work on modern drives. Yes?
You discussed the wrong way to format a drive using the deceptive commands.
Yes.
And I'm familiar with one correct way, and that's a low-level format, but that takes a very long time.
So the whole question of low-level format, that's a very early 90s term.
How about zeroing the drive? Let's
Right.
use that term.
So zeroing the drive is great. You start at the beginning of the drive, and you write dev 0 to the end of the drive. And it takes somewhere between 10 minutes and 30 minutes, and it's
Okay.
great.
That's not
Now,
too bad.
Peter Gutman has this paper that is heavily cited saying you need to do 35 passes, and that's misciting the paper. So he says that you never need to do 35 passes because that's for all the different versions of drives. And the postscript on the paper says that for modern hard drives, he believes that just 2 passes of random data is completely sufficient. Coding has gotten up so high that we believe that data cannot be recovered after 2 passes of random data. And I believe that for any technology that is accessible to most people, that a single pass of zeros is sufficient. I've never seen otherwise. And I'd very much love to see some open, unclassified research that shows that you can recover data that's been overwritten once on a modern hard drive. It's clear you can do it on a circa 1985 floppy disk. But modern hard drives are much better than 1985 floppy disks. And we just don't know. But for the adversaries that I'm considering, zeros are fine. Zeros are actually better than random data because you can audit a drive filled with zeros and know that it's filled with zeros. But if you audit a drive that's filled with random data, it's really hard to know if it's random or if it's encrypted. It could just be that somebody encrypted all the data on the hard drive with a key that they know and you don't. So you still have that problem. So this says 5:21. What time do we have to vacate the room?
There is a class coming in the next 10 minutes.
Okay, so we have 4 and 5 minutes. Any other questions? No? Wow.
Thank you, Simson.
Well, thank you.